I kind of like it better. So that's some value. Okay, so this one says we're looking for the limit as x goes to 1 of f of x minus 4 over x minus 1, and actually they tell us that this is 2. And the question is, what happens as x goes to 1 of f of x? So this is a little different kind of problem, right? We sort of know what the limit is, but we don't necessarily know what the function is. So let's sort of think of a hypothetical here. Notice as x goes to 1, the bottom or the denominator is certainly going to 0. What if this top was going to a number like 3 or negative 0.002 or any number? Can you see that if this top was going to anything that's not 0, this ratio would be then a vertical asymptote or an infinite limit, right? If the bottom is 0 and the top is not 0, this wouldn't equal 2. This would be an infinite limit. So the only way that this limit here is equal to 2 is if this limit on the top is going towards 0. So that tells me that the limit as x goes to 1 of f of x minus 4 has to equal 0. And one of our rules of limits is that as long as both the limits exist, I can take the limit of each piece separately. The limit as x goes to 1 of 4 is 4. So when I move that over to the other side, right, that's 4. I get this. The only way that that limit could be 2 is if f of x is actually going towards 4. And this really touches on the idea of infinite limits and how a sort of indeterminate form could equal any value. In this case, 2. Okay. Yeah, okay, thanks for the feedback there. Yeah, I don't know, I feel like maybe my technology is lacking or something, right? My digital pen doesn't seem quite as nice as my physical pen. Okay, so it's a couple kind of questions, ideas about limits, some conceptual ideas about limits, a little bit of a review of some strategies. Okay. So what I'd like to talk about today is continuity. So this is 2.5, continuity. And as always in math, we have to make some definitions first. We got to define what it really is we are talking about, and we have to define it very carefully. And so here's our definition. F of x is continuous at x equal a at some point if the limit as x goes to a of f of x equals f of a. And you may recognize this. It looks a little bit like, well, it looks sort of exactly this line right here of what we talked about with direct substitution for limits. There's a
relationship there between those two things. But for right now, it's really best to just think of this as the definition of what it means to be continuous. Now, you guys maybe already have kind of an idea of what it means to be continuous, right? But your idea is sort of fuzzy because you wouldn't have had this limit definition. And so you certainly would be able to tell me some things are or some things are not continuous. But notice continuity is what's called a pointwise property. What that means is that you can't really say a function is not continuous or is continuous. You have to talk about it in terms of each point, right? So you can say it's continuous at 2 or not continuous at 5, depending if the limit equals the function value. And just to show you how this definition sort of meets what we would expect about continuity, let's look at a couple examples where a function fails to be continuous. So here's one example. Let's say I have a function like this that has a hole at a. I think we could all agree that that's not continuous, right? It has this gap in the function, so it's not what anyone would think of as being continuous. And what would happen is if you tried to test this function using this definition, you would notice that f of a does not exist. So right there, you would fail. This is not possible. You can't have the limit equal to f of a if f of a doesn't even exist, right? So that's one possibility that we kind of rule out by stating this definition. Well, you could also have the situation that looks like this, right? There, f of a certainly exists, so that's fine. That's a good start. But we see very clearly that the limit there does not exist, right? So in this case, the limit as x goes to a of f of a does not exist. So again, doesn't look continuous at a, and it's not because it can't satisfy this equation. And then finally, we could also have a situation where the limit exists and the function value exists. But of course, in this case, they're two different things, right? The limit is down here, the function value is up here, so therefore that also wouldn't satisfy my requirement. The limit as x goes to a of f of x in this case would not equal f of a. So again, these are just specific examples of things that aren't continuous and how this definition would identify those or tell us that it is not continuous at that point. There are other situations, and if we have time, we will sort of talk about one of those unusual situations and see if we can, that will help us understand continuity a little bit more. What about this example? Oh, there we go. I think I froze up for a second. What about this example? What about this function? So continuous. We write continuous a lot, so we will abbreviate that sometimes. Is this function continuous at x equals a? Let's think about that. It's sort of a, I mean, there's a clear answer here, but on one hand, it's sort of continuous, right? I mean, it doesn't like have any of these obvious holes and jumps and things where, you know, a lay person, a person on the street would say, oh, clearly that's not continuous, right? But for us, we have to make sure we're going back to our definition, right? So what does our definition say? Our definition says the limit of the function has to equal the function value. Well, what's the limit as x goes to a of f of x? And I didn't give you any actual values here, right? Let's say this is 3. Remember, for the limit to exist, what we saw yesterday is that we have to look at a little interval around a, but we have to look on both sides. And the function doesn't even exist for values on the right side of a. So there's no way that this limit here can even exist. We have to be able to look at both sides of the point, right, of the x value. So this limit does not exist. So this is a no. This function is not continuous at x equal a because the limit doesn't exist. But I think you'd be well within your rights to say, but okay, maybe it doesn't quite meet that condition, but like, what about if you had a situation like this? Like that bottom function, that one's very clearly not continuous, right? Because it's like got this hop or jump in it. Whereas this upper function, it feels kind of like it kind of should be continuous, even though it doesn't quite meet our definition. So what we do is we make a distinction here and we have an endpoint, and we introduce this idea of one-sided continuity. So we're going to say f of x is continuous from the right at x equal a if the limit as x goes to a from the right of f of x equals f of a. And of course, from the left is the mirror image of that, right? We just say from the left and make it an a to the little negative there, right? A from the left. So here, looking at these two scenarios, this top one would be continuous at x equals a from the left, right? The one-sided limit matches up with the function value, and that's kind of good, right? We are a little prejudiced. We prefer continuous functions. In the bottom function, that doesn't work, right? The limit, the one-sided limit and the function value are different, so this is not continuous from the left. If you're not continuous from the left, then you're not continuous at all. So we have continuity, and then we can refine that a little bit to one-sided continuity, and we can kind of put all that together to say f of x is continuous on a closed interval. So this is a lot of times how we like to talk about continuity, is we're going to say it's continuous on a closed interval. So that means everywhere between a and b and also including a and b. And what we mean by that, it's continuous on this closed interval if f of x is continuous on the open interval a to b. So that means it's continuous everywhere except the endpoints. That's number one, and you can just use regular continuity for that. And f of x is continuous from the left at x equals b and from the right at x equals a. So basically all that's saying is we just want to be very clear when we say continuous on a closed interval, we mean really that it's continuous everywhere inside, and then on the endpoints, we have continuity from the left to the right. So we don't have this situation, right? That's not continuous. We have this situation, right, where it's sort of stops and includes its endpoints. So when we talk about continuity on an interval, we're really talking about continuous at every value in that interval. Okay. Questions so far? Okay. All right, so continuity continued. All right, so some of you, well, I don't know if you are or not, but you might be considering how this connects to our direct substitution property, because that really is exactly the same statement, that the limit is equal to the function value. And the sort of origins of those are connected. What we'll learn in this section as you look through it is that if f and g are continuous at x equal a, then f plus g, f minus g, f times g, constant times f, f divided by g, as long as g does not equal 0, are all continuous. So what this says is if you start with two continuous functions, you can add them and subtract them and multiply them and divide them, multiply them by numbers, and you don't change continuity. And that really comes from the fact that continuity is a limit, and you can do all of these things with limits without sort of messing up the limits. Okay, so we could prove this in some detail, but it's really fine to just have a sense that the properties of continuity flow from the properties of limits. Okay, so since limits work a certain way, continuity is a limit, continuity works that certain way. It also turns out that really most of the standard functions that we work with are continuous on their domain. So it turns out that trig, polynomial, rational, logarithmic, exponential functions are all continuous on their domains, meaning where they're defined. So certainly rational functions and trig functions aren't defined anywhere, and if they're not defined there, then they're not going to be continuous there, right? Because the function has to be defined. But as long as they're defined, they are going to be continuous. None of those functions have built-in things like this or like that, right? They don't have these gaps and jumps and holes. They're just you know, continuous functions. Okay. So this we can use as a fact, and if you're working with continuous functions, remember, of course, that means the limit as x goes to a of f of x will equal f of a, which is direct substitution. So this is really telling us that we can use direct substitution to calculate a limit as long as we are working with a continuous function. It's saying the function value and the limit are going to match up. And that's actually what a continuous function is where the function and the limit match up. Now, most of the interesting functions that you'll be working with and seeing with are not going to be defined at the values you're interested in. So you're not going to be able to use direct substitution immediately. You're going to have to do some algebra to change it around or something else like that. And then the other strategy is that we can also have piecewise functions, right? Functions where we have two different halves that come together, right? And those are always sort of unclear as to whether those are continuous or not. So like, for example, let f of x equal x squared plus 2 if x is less than or equal, or just let's say if x is less than 1. Well, could do something maybe more interesting, but let's try cosine of pi x plus 4. Is f of x continuous at x equal 0? Well, at x equals 0, we are very safely under this bound. So we're very clearly, well, not very clearly, but we are working with x squared plus 2. X squared plus 2 is a polynomial. All polynomials are continuous on their domain. So a good answer would be just yes, f of x is polynomial. Okay. At that point, x equals 0. What about x equals 2? Same argument. Very clearly, x equals 2 is bigger than 1. So it's this function. This is a trig function. And you don't even have to calculate it. Cosine is defined everywhere. So this is, yes, f of x is a trig function. In fact, it's a trig function plus 4, but that's not going to change it either, right? You can add or subtract continuous functions. So the real question, the most interesting question is, what about at x equals 1? Is it continuous at x equals 1? Well, as I've written it, it is not, because what is f of 1? I didn't even define f of 1. There's a hole in this function at 1. It's not defined. So no chance of being continuous. So let's fix that. So is this function now continuous? Now we do have an f of 1, right? F of 1 is 1 plus 2, which is 3. So is it continuous? Because f of 1 equals 3? Not necessarily, right? That's not the definition of continuity. It's not that f of a, right, or f of 1 exists. It's that the limit and the function value are equal. That is what you have to show if you want to show continuity. So I also need to figure out the limit as x goes to 1 of f of x. And since this is a piecewise function, I'm going to have to look at that limit from both sides. That's the way I'm going to evaluate that particular limit. As I come towards 1 from the left, that's up here. So the function will look like x squared plus 2. As long as I'm coming from the left of 1, I don't have to worry about the other half of this piecewise function. And this is a nice polynomial. As we verified before, you can find that by direct substitution. You really already know that. It's going to be 3. As I come towards 1 from the right, that's the cosine of pi x plus 4. If I put in 1, again, direct substitution works because this is a trig function. It's going to be continuous on its domain, so its one-sided limit is going to equal its limit. As I put in 1, I get cosine of pi. Cosine of pi is -1 plus 4. That's 3. Since the left and right-hand limits are the same, it's 3. And that is equal to the function value, which is 3. So it is continuous at x equals 3. Okay. So this function, it turns out, is continuous everywhere. I know that anything less than 1, it's continuous because it's a polynomial. Bigger than 1, it's continuous because it's a trig function. And it is continuous at 1 because, well, I just showed it, why it's continuous at 1. So you need to be careful that you're actually checking the conditions for continuity. Okay, you cannot just assume it's continuous if it's a piecewise function like this. You actually have to check the limit and make sure it equals the function, unless you know something, right? Like that it's polynomial or a rational function or something like that. Okay. Questions about that? It turns out continuity is a really important property for us throughout this course. So a lot of our theorems and rules and requirements of functions will need the function to be continuous in order to work. And you'll see that from right now till our last couple sections, right? We will need continuity throughout the course. We get to assume a lot of things are continuous, but not always. And we need to understand what we're really saying when we say something is continuous. So just to make sure that we have due respect for continuity, I'm going to show you a little example of an unusual function and try and explore its continuity. This is one I would often have everybody kind of work on together if we were in class, but we can I'll kind of talk through it with you here. So I'm going to define f of x like this. I'm going to say f of x equals x squared if x is rational. And remember, rational numbers can be written as fractions, 1/3, 2, 157 over 29, etc. Right? All those are rational numbers. And I'm going to say it equals 0 if x is irrational, not rational. And it turns out that rational numbers and irrational numbers are what we call dense. Dense means that if you take any little slice of the number line, no matter how small you take that little chunk, within that chunk there are going to be infinitely many rational and irrational numbers. Sometimes we get fooled by thinking there are lots of rational numbers because we see them more often, but there are actually way more irrational numbers. We just don't bump into them as much. So irrational, like square root of 2 and pi, are some kind of special irrational numbers, but there's infinitely many of them, and they are interspersed or dense within the number line. Okay, so you can't escape rational or irrational numbers, no matter how small you try and take a chunk out of the number line. So this is kind of a piecewise function. I mean, I guess it is a piecewise function. It's just broken up in a different way, right? Rather than having like solid intervals that fit together. Here, the pieces are like blended together, right? Like the intervals got all blended and mixed together. So I have both rational and irrational numbers. So it turns out we can't even really graph exactly what's going on because there's, you know, infinitely many rational and irrational numbers. But if we imagine kind of moving along the x-axis, f of 1 is a rational number, so I get 1 squared, which is up here. 0 is a rational number, so 0 squared is right there. And as I pick out more and more rational numbers, what we would get is, you know, this part of the parabola. Right? And I'm drawing dots, even though there are infinitely many of them, to show that it's kind of like jittery or perforated, right? Because within these, every time I move along the number line and hit an irrational number, I'm just going to get 0. So at the same time, I also get all of these dots along the line f of x equals 0, right? And of course, this extends to the other side as well. So I've drawn it with a bunch of dots, but of course it would be so dense and solid you wouldn't actually be able to see those dots if it were somehow accurate. Okay, so this is this kind of weird function, and the question is what's going on with this function? So here's the first question. What is the limit as x goes to 0 of f of x? And the second question, what's the limit as x goes to 1 of f of x? And I'll tell you what I'm going to do here is I'm going to write up a few questions here, and then I'm going to experiment by dumping you into some breakout rooms. And your job in the breakout room is to turn on your mic and you can discuss this briefly. I'll give you like 2 or 3 minutes, okay, just to kind of talk it over. You can say hi to each other and talk about me if you want to, whatever, but just kind of make a little small talk. See if you have any ideas, guesses about what you think these limits are. So the limit as x goes to 0 of this function, the limit as x goes to 1 of this function, and the third one will say, what's the limit as x goes to, say, a, and this is for a not equal to 0. So what do you think the limit is for any number that's not 0? You may or may not be able to make much progress on it, but let's just experiment and see if we can come up with some ideas. So let's try this. That should work. Let's try it. So go ahead and jump into that breakout room. I'll pull you back in just a couple minutes. You can say hi. I'm gonna switch you guys around a little bit.
quick one. Yes.
Okay. So we'll try and do that a little more often. Sort of bump you in, give you a chance to just talk briefly rather than just hear me talk on and on about these things. And maybe we'll have some activities too that will help do some work in those breakout rooms. And I'll often kind of pop in and say hi. I didn't get to anybody's this time. So, okay, so I'll give you the results here of this. So as x goes to 0, it turns out that the limit of f of x is actually 0.
Mhm.
And you can see this probably most easily by the squeeze theorem, if you remember the squeeze theorem. The squeeze theorem says as long as I can bound my function by two other functions, and there's many options for the bottom function, but I could just use this, right? F of x is always less than or equal to x squared, and it's always bigger than or equal to 0. Right? It's jittery. It's really hard to control and contain what's going on otherwise, but I know it's at most x squared and it's at the smallest 0. And of course, both of those have limits that are equal to 0. So that's a, you know, I wouldn't expect you to be able to deal with some weird function like this on a test or a quiz, but that is one where the squeeze theorem is sort of manageable in that case. What about the limit as x goes to 1 of f of x? And the problem here is that if you think about your kind of delta epsilon, if someone gives you a little target, right, let's say you think the limit is 1, someone gives you a little target around 1, no matter how small you pick your interval around 1 here, you're going to get some irrational numbers that are going to fall down at 0. And you're going to get some rational numbers that are going to fall up here. So you cannot force the function to be inside of this target no matter how small you pick your delta. You cannot find a delta for this particular epsilon. So this limit does not exist. And the same thing holds if you tried to make the limit 0, right? You have some values that are up here and some values that are down here, no matter what interval of delta you choose. And in fact, it's not distinct to 1. That same thing happens every other value, right? No matter how close you are to 0, there's still a little space between the x squared function and the 0 function. So as long as you're not looking at 0, this limit does not exist. So this is a function where the limit doesn't exist anywhere except at one point. Okay. It's a little weird. It's not maybe how we think of limits, but that's what this function does. Now, if we had a little more time, I might put you back in groups to talk about this one, but it doesn't take as long to talk about this one. Is f of x continuous at x equals 0? Is f of x continuous at x equal 1? And finally, is f of x continuous at any x equal a not equal to 0? Why don't I just do that? I'll just kick you right back into groups here. I'll give you just a minute. And think about your answer and what you know about continuity. Okay. Did that, hopefully that sort of worked, at least to like bump in and out of breakout rooms. Again, feel free to let me know in the chat privately or publicly, whatever you want. If that was effective, we can do more of that moving forward. Okay, so is the function continuous at x equals 0? Notice, like, if you really just sort of intuitively looked at this function, it wouldn't feel actually like it's continuous at all, right? It's like bumpy and jittery in like the worst possible way. But it turns out it quite easily meets our definition of continuity. The limit of the function is 0, and f of 0 is 0, right? If it's irrational or rational, it's x squared, right? It doesn't matter. But 0 is rational, so 0 squared is 0. So it is continuous at x equals 0. The function value equals the limit. How about at x equals 1? Well, you can see that fails, right? Because the limit doesn't exist. If the limit doesn't exist, it cannot be continuous. Is it continuous at any value outside of 0? Well, same argument, right? The limit doesn't exist there, so it can't be continuous. So what we have here, f of x is a function that is continuous at only a single point. Maybe I should put that with exclamation points afterwards. Because that sort of doesn't seem to work, right? Like continuity doesn't feel like something that can exist at just a single point, right? We imagine it as like a smooth curve, all these points sort of linked together. But as I said in the beginning, continuity is a pointwise property. It is either true or not true at individual points. So it is quite acceptable to have a function like this that is continuous at one point and not continuous anywhere else. And you know, the illustration here is that even an idea that maybe seems relatively straightforward, like continuity, if you've had some experience with it before, when we get into unusual or special circumstances, we really need to fall back on the definition. Our intuition is not going to be enough to deal with functions like this, right? We need to fall back on those definitions. So when you're asked about continuity, verify the conditions. And the conditions are that the limit exists and the function exists and the two are equal. If you show that's true, then you've shown that it is continuous. Okay. All right. So that's what I had for today. Should get you through most of 2.5, but again, you know, check the lecture capture and the small videos. You know, this work here is similar to the lecture capture. You may find some similar problems that you know, may be able to skim through, but there'll be some other different problems too. So it's worth looking at that as well, especially if it's a topic that's giving you any trouble at all. So I will stick around if there are any additional questions. Otherwise, nice to see and hear you all, and have a great weekend.
Yeah, I have a question real quick.
Yes, ask away.
As far as the labs go, is that just something that
Yeah.
we start doing on our own, or?
No, good question. I will send that out in our schedule. I think the next schedule, I'll give you some information about the labs.
Okay.
So I think the topic for the first lab really is in chapter 3. So it'll be in maybe two weeks or so. We'll start up with the labs.
Okay.
So yeah, don't worry about those right now, and just focus on the homework and the take-home quizzes.
All right, thanks.
You're welcome. Hi, Riley, are you there?
Yeah, I'm here.
Hi, how is it going?
Hi. Good.
Good. Yeah, I got obviously good, you got the email that I sent. I saw the email and the request, but I didn't really know what your situation was. So just to make sure that the switch would work for you, can you just tell me a little bit about